Until now, we had set up the Fourier series in terms of trigonometric functions. Now there is an alternative way of setting up the Fourier series. This will be in terms of exponential functions. So if you recall, x of t is equal to a naught plus sigma n is equal to 1 to infinity a n cos of n omega naught t plus sigma n is equal to 1 to infinity b n sin n omega naught t. So this is the exponential Fourier series. Okay. So this x of t had been written in terms of this trigonometric functions cos n omega naught t and sin n omega naught t plus the constant term a naught. Now we can express sine and cosine in terms of exponential functions. We know that cos theta is equal to e to the j theta plus e to the minus j theta by 2 and sin theta is equal to e to the j theta plus e to the minus j theta by 2j. Therefore, x of t can be written as, you put a naught as it is, plus sigma n is equal to 1 to infinity a n e to the j n omega naught t plus e to the minus j n omega naught t divided by 2. Okay, plus sigma n is equal to 1 to infinity b n e to the j n omega naught t plus e to the minus j n omega naught t, divided by 2j. Okay, now we have e to the j n omega naught t term here as well as here. Okay, so let's group them together so that we write this series in terms of exponential functions. So let us group a naught plus, see here I have e to the j omega naught t, here also I have e to the j omega naught t. What is the coefficient of e to the j omega naught t here? bn, and here an. So I can group these two guys together. So sigma n is equal to 1 to infinity an by 2 plus bn by 2j times e to the jn omega naught t. Similarly, I can combine the e to the minus jn omega naught t term. So n is equal to 1 to infinity oh my god, it has gone. Okay, bn by 2j times e to the jn omega naught t plus sigma n is equal to 1 to infinity. You combine this negative exponential. So again an, is it plus? This one is not plus. Okay, so this one is minus. So an by 2 minus bn by 2j times e to the minus jn omega naught t. Now an by 2 plus bn by 2j can be written as an by 2 minus j times bn by 2. If you bring the j to the numerator, then it becomes minus. So I can write an minus j times bn by 2, this one. Similarly, this guy can be like an by 2 plus j times bn by 2. Therefore, the above series becomes a naught plus sigma n is equal to 1 to infinity an plus j times bn whole divided by 2 times e to the jn omega naught t plus sigma n is equal to 1 to infinity an plus plus or minus plus only, because already I have one minus, and then this j becomes minus, so it will be plus. But here I think this is minus, right? I'm sorry, this guy is minus an plus j times bn by 2 times e to the minus jn omega naught t. So like this you can get it now. Now what we have done is express x of t not in terms of trigonometric functions but in terms of exponential functions, and here also we have exponential functions, okay, of the type e to the jn omega naught t. Now in the context of this exponential functions, we would like to indicate the coefficients in a different way, not like an minus j beta n by 2 like this or like this. We will give some name for this, some notation. So let us assume let an minus j bn whole divided by 2 is equal to cn, then an plus j bn by 2, what will happen? This guy becomes cn star, cn conjugate, okay. Therefore the star indicates complex conjugate, okay. So since we are giving the symbol c for the various coefficients, we may call this this guy we may call as c naught. Therefore an minus j times bn is equal to 2 times cn, and then an plus j times bn is equal to 2 times cn complex conjugate. So that is a notation that will follow. So remember these two things. Why I brought this 2 to the right hand side, I will tell you in a minute, okay. There is a special reason for that. So an minus j bn is equal to 2 times cn, an plus j bn is equal to cn complex conjugate. Okay, just to indicate this is a complex number, okay, this is the complex number. Let me put a number, you put like this bar also, but that is not also needed. Therefore the above expression becomes x of t is equal to a naught is replaced by c naught plus sigma n is equal to 1 to infinity cn e to the jn omega naught t plus sigma n is equal to 1 to infinity cn complex conjugate of e to the minus jn omega naught t. Okay. Now we know that cn is equal to cn is equal to c minus n complex conjugate. This you can prove it. Okay, so you take cn, then take complex conjugate, and then becomes, you replace n by minus n, then it will be same. These two will be equal. cn is equal to c minus n complex conjugate. Therefore in this what you do, you replace, let n is equal to minus m, then what will happen? The whole expression is going to be sigma m minus m is equal to 1 to m is equal to minus 1 to minus infinity. You can work on it, okay? So just I am skipping some steps here. And let n is equal to minus m, then what will happen? Like the lower limit is n is equal to 1, therefore m is equal to minus 1, and the upper limit is n is equal to infinity, then m becomes minus infinity. Then cn conjugate becomes c minus m conjugate, right? Then e to the minus j n omega naught becomes e to the plus j m omega naught t. Therefore this expression I can write as x of t is equal to c naught plus sigma n is equal to 1 to infinity cn e to the j n omega naught t plus sigma m is equal to minus 1 to minus infinity c minus m conjugate e to the j m omega naught t. After all, in the summation, m is a dummy variable, right? The dummy variable you can replace by any other variable which you like, as I already told you. Therefore x of t is equal to c naught plus sigma n is equal to 1 to infinity cn e to the j n omega naught t plus sigma m is equal to minus infinity. I can interchange a plus b equal to b plus a, right? M is equal to minus infinity to minus 1, not m, n. I can replace n. So two things I am doing here. One is interchanging, changing the limits and changing the dummy variable. So n is equal to minus infinity to minus 1 c minus n complex conjugate e to the j n omega naught t. Now what is this c n complex conjugate, c minus n complex conjugate? Again it is c n. Therefore c naught plus sigma n is equal to 1 to infinity c n e to the j n omega naught t plus sigma n is equal to minus infinity to minus 1 c n e to the j n omega naught t. Now here also cn e to the j n omega naught t, here also same. You combine these two summations. This guy is okay, 1 to infinity, and this is minus infinity to 1. So this point is 0, and that 0 term is c naught. Up to here minus infinity to minus 1 is this range is given by this summation, and from 1 to infinity let's say this range is given by this summation, this guy. So we can combine everything together and put one summation. So sigma n is equal to minus infinity to plus infinity cn e to the j n omega naught t. This is x of t. So here we observe that c minus n is equal to cn conjugate. Okay, so that means a plus j bn by 2, this is my cn conjugate. Now if you replace n by minus n, since bn is an odd function and a will not change, you can prove this. Take a formula and bn formula, then you can prove this. It is very simple. So I leave it at that point. So this is a compact way of representing the Fourier series. Compact form of Fourier series. So you do not have groups of terms like a naught, then an and bn like that, and so on and so forth. You have to deal with a single set of coefficients, that is cn. So it is a compact form of Fourier series. The question is, how is the Cn related to An and Bn? What is the relation between Cn and An, Bn? What is the relation among these three things? So we defined Cn is equal to An minus j times Bn by 2. So what is Cn now? If you take magnitude of this, then this is going to be square root of An square plus Bn square whole divided by 2. Therefore, square root of An square plus Bn square is equal to 2 times magnitude of Cn. So in anticipation of this notation only, we put a 2 here. Otherwise, we could have defined simply C. So the C comes because of that only. Now the next question that we would like to ask is, how do we evaluate this Cn coefficient? Evaluate Cn coefficients. What is the formula for that? In the same way as we have done for the trigonometric Fourier series, trigonometric functions, we can apply here also. So this can easily be derived as follows. We know that Cn is equal to An minus j Bn by 2. That means An by 2 minus j times Bn by 2. We know the formula for An and we know the formula for Bn. Substitute the formulas and you will get the answer. Now let's do it. Cn is equal to 1 by 2 times An minus j by 2 times Bn. This is a formula. Now 1 by 2 times, what is An? An is 2 by T naught integral of 0 to T naught x of t cos of n omega naught t dt minus j by 2 integral of 2 by T naught, right, 0 to T naught x of t sin n omega naught. That is 1 by 2 by T naught integral. Now this 1 by 2 is constant, 2 by T naught is constant, 2 and 2 will get cancelled. So 1 over T naught is constant and you put a single integration 0 to T naught, and here x of t, I can take x of t commonly outside, then cos of n omega naught t minus sin of n omega naught t multiplied by dt. What is, no, there is a j term here, this j term I forgot, j. There is a j term. Now cos theta minus sin theta, this is e to the j n omega naught t. Therefore, your expression is going to be 1 over T naught integral of 0 to T naught x of t multiplied by e to the j n omega naught t. Is it plus or minus? Minus, because there is a minus symbol here. It is very dark color. Let me use fluorescent yellow. Minus, here also put minus. Therefore, one more minus will come here also, times dt. So this is your Cn. So the integral that needs to be carried out to evaluate the Cn is like this. So this is really the average of x of t multiplied by e to the minus j n omega naught t. So now what do we observe here in this formula? What are the merits of this exponential form Fourier series? First of all, we observe that we have only one single formula. There we had two formulas, but here only one formula. Only one formula for evaluating the various Fourier coefficients, and we do not have separate formulas for there we have in fact three formulas. one for a naught and another one for an and another one for bn, but here we have only one formula. Okay, and there we had three formulas separately, and the notation is very simple and very compact. More importantly, when we extend this concept of Fourier expansion, later on we will expand this Fourier series to study about Fourier transform. That time this exponential form of Fourier series will be very useful than trigonometric form of Fourier series. Okay, so the exponential form of Fourier series is very much useful for us when we study Fourier transform, continuous time Fourier transform, discrete time Fourier transform, discrete Fourier transform, and so on and so forth. So therefore, exponential Fourier series is much useful to study continuous time Fourier transform, discrete time Fourier transform, then and so on. Maybe of course it depends. I can say, let's say, continuous time Fourier transform, then trigonometric Fourier series. Okay, so that is another advantage. Okay, this experiment, because Fourier integral concept, which we will take up later after some time, there these expressions for Cn can be in a straightforward fashion extended to the Fourier integral, that is Fourier transform. So we have a single formula valid for all n. Okay, here this n is, and one more important point is here in this exponential Fourier series, if you look at the formula, the range is from minus infinity to plus infinity. But if you look at trigonometric functions, then n is equal to 1 to infinity. Look at this is another difference, and I will tell you why this difference comes in a minute. And the notation is compact, and the notation can be extended in the Fourier integral, I mean Fourier transform, quite conveniently. So that is the important thing when you work on exponential Fourier series. Okay, so x of t is equal to sigma n is equal to minus infinity to plus infinity, then Cn e to the j n omega naught t. In the formula, the minus sign will come. Okay, look at here, there is a minus sign here, but in the series there is a plus sign. Please note down the difference. When you calculate Cn, it is 1 over t naught integral of x of t e to the minus j n omega naught t dt, but here it is plus. Note down. So in the Fourier series expansion for this, like exponential form of Fourier series, we note that each term by itself may not convey any physical signal. In the trigonometric functions, yes, because we have cos n omega naught t and sin n omega naught t, both are real signals, so it has some physical meaning. But when I take, let's say c1 times e to the j omega naught t, what is the meaning for this? Physical meaning. There is no physical meaning for this, because as I said in the laboratory, you cannot generate this e to the j omega naught t, because when you substitute a real value of time, see this t here, exponent has t, and if you substitute, let's say t equal to 1 second, then it will not give any physical meaning. Okay, a real value of time, this each term by itself will not yield a real value for the function. However, see this is a summation, it goes from minus infinity to plus infinity. That means what? If you have c minus 1, definitely you will have c plus 1. If you have c minus 2, of course you should have c2, c plus 2, c minus 3, c3, both are complex conjugate. For c1, you have c1 times e to the, I am sorry, hold on 1 second. If n is equal to 1, then definitely you have n is equal to minus 1. So the corresponding components are c1 times e to the j omega naught t and for minus 1 c minus 1 e to the minus j omega naught t, and these two guys are complex conjugate. If you combine these two guys, then you will get a real signal, e to the j omega naught t plus e to the minus j omega naught t. Similarly, if you substitute n is equal to 2 and n is equal to minus 2, again you will have c2 times e to the j2 omega naught t, then c minus 2 times e to the minus j2 omega naught t. You combine these two guys, again you will get another term. See, suppose if you combine these two guys, then 2 times c1 times cos of omega naught t plus some phase angle theta 1, that we can find out very easily. So, combine the positive index and the negative index, these two together will lead to a real function of time, a sinusoid, which will be 2 times cn times cos of n omega naught t plus theta n. Like as I said, e to the j omega nt, it is a complex signal, and this cn also complex. Okay, if it is a complex, then you can represent in terms of magnitude and phase. Let's say cn, I can represent cn magnitude, then its phase will be e to the j theta n times e to the j omega naught n. Now this is cn magnitude times e to the j times omega naught nt plus theta n. Similarly, for the negative term c minus n is equal to c minus n, then e to the minus j theta, c minus n is equal to e to the minus j n omega naught t. I am writing cn in terms of magnitude and phase times e to the minus j n omega naught t. Then you combine c minus n constant magnitude e to the minus of j n omega naught t plus theta n. Now combine these two guys, mod of cn is equal to mod of minus cn, that you can prove how it is a plus j bn by 2. Okay, therefore if you combine these two guys, then 2 times mod of cn cos of n omega naught t plus theta n. So the amplitude of the nth harmonic component is this magnitude. What is that magnitude? Square root of an square plus bn square. Okay, so this is a real formula, real function of time, real function of time. Okay, but if you take individually this guy and this guy individually, if you take individually, then they are not a physical signal. But when you combine them, when you combine these two, then this guy and this guy, when you combine these two, you will get a real signal. Okay, now let me consider one example. For this, let us work out an example, okay, illustrating the exponential form of series, exponential form of Fourier series. You can take the same example which we take some time ago in one of the previous lecture. We have worked out earlier in one of the previous lecture, a square wave like this, a square wave. Let me call this is x of t. Now we would like to find its Fourier series expansion in the exponential form. Okay, so what is your cn? Cn is equal to 1 over t naught integral of 0 to t naught, then x of t, mind you there is minus here, minus j n omega naught t, and the signal is like this, 0 to t naught by 2, let us say this is a, and t naught by 2 to t naught, the magnitude is minus a. Therefore you split into 1 over t naught, split into two integrals, 0 to t naught by 2. In that interval the x of t is a times e to the minus j n omega naught t plus 1 over t naught by 2 to t naught, minus a times e to the minus j n omega naught t and dt. Now again this simple integration, okay, a naught is constant, you can pull out and do all the simplifications, then you will end up 2a times minus j n omega naught t naught, I am writing the final answer, is e to the j n pi minus 1. Now if you substitute n equal to 1, then e to the pi, e to the j pi minus 1, minus 1, minus 1, minus 2, so minus 4 pi you will get it. And omega naught t naught, again you simplify this, then this is equal to 0 when n is even, and minus j times 2a times n pi when n is odd, because this e power j n pi is either plus 1 or minus 1 depending upon the value of n. So, since we know that Cn equals an minus jn, Cn is equal to an minus j times bn, then Cn is given by what? Minus j 2a by n pi. On the right hand side you have an minus j beta n. You compare real terms and imaginary terms. I can put a 0 minus like this. So the real term is 0. So compare term by term, real and real, imaginary and imaginary. Well, therefore what is bn? Bn is equal to 2a by 2 pi. So this agrees with what we calculated in the previous lecture. Please compare with the previous class. So we found that bn is equal to 2a by 2a, sorry, this is not 2, this is n pi. Please remember n pi. So this result we have already obtained, okay, from the trigonometric form of Fourier series. So this ties up with the trigonometric Fourier series. Of course, C naught equal to 0. Why? Because it is area, positive area is equal to negative area. This positive area must be equal to negative area. So C naught is 0. So when you are carrying out this analysis to find out Cn, it would always be advisable for us to arrive at the C naught value independently. Don't substitute here n equal to 0 in this expression. Where is it? Here. We said Cn is equal to 0 n even and minus j 2a by n pi and n odd. Okay, don't substitute n equal to 0 in this expression, you will get a wrong answer. So C naught you have to find out separately using the formula, like Cn is equal to 1 over t naught integral of e to the minus j n omega naught t times x of t dt. Now substitute n is equal to 0, then C naught is equal to 1 over t integral of x of t times dt. You have to find out separately this one, because sometimes when n equals 0, it leads to some difficulties. In case if you put n equals 0, then you will get infinity, Cn becomes infinity, so that's wrong. So it is always advisable to calculate C naught independently rather than substituting n equals 0 in the Cn expression. Don't do that. Okay, sometimes it may work, sometimes it may not. Okay, so we have discussed in one of the previous lectures we have discussed the symmetry conditions in relation to an and bn. Similarly, here also we can discuss some symmetry conditions. Now, what are the similar conditions that are applicable to the Cn coefficients? Okay, anyway, let us discuss now symmetry conditions. Okay, now the first one is if x of t is even, then Cn is real. Okay, that is very easy to remember. If x of t is even, then we said that only cosine terms survive, right? Cosine terms survives. That is bn term is equal to 0 and an term is not equal to 0 if x of t is even. Therefore, what is Cn? Cn is equal to an minus jbn, that is an plus 0. So there is no imaginary part, right? Therefore, if f of t is even, it means that bn is equal to 0. So this is a real part. So cn is equal to an. What is an? An is a real number. It's a number. I don't have the imaginary. Imaginary has disappeared now because of bn is 0. Okay. The angle associated with the complex number is 0 because tan inverse of b by a. Tan inverse of b by a, then tan inverse of 0 by a, which is again 0 degree phase angle for Cn. Cn equal to, angle of Cn equal to 0 degree, and Cn is real if x of t is real. Okay. So similarly, if x of t is odd, the same argument you can apply here, then Cn is purely imaginary. Why is it purely imaginary? Because if it is odd, then a0 and an is equal to 0, right? If the signal is odd, we know that Cn is equal to an minus jbn, and this guy is 0. So Cn is only purely imaginary number only. Therefore, Cn is imaginary. And the third property is, this is second property, and the third property is, suppose if f of t is no half-wave symmetry like this, x of t is equal to minus x of t plus t naught by 2, then Cn can exist only for odd n. Okay, that means what? Even harmonics absent. Even harmonics absent. Okay. That is, Cn can exist only for odd n. Even harmonics are absent. Okay, so that's it. So we will discuss from this point in the next class. Let me stop at this point. Thank you very much.